Thanks again for joining. I'm Mary, and I'm here to introduce Sundial, a project a couple devs and I built this fall. Here's the team: David, Jacob, myself, and Sofia. Sundial is a self-hosted open source cron job monitoring and management service that can operate across one or multiple nodes. I'll briefly go over the agenda. Today we'll be talking about what cron is and its challenges, and an introduction to Sundial, how Sundial monitors, how Sundial manages, a demo of how Sundial works, and finally, load testing and future work. First, let's explain what cron is. Cron is a command line utility available on Unix and Unix-like operating systems. First created in 1975, it is a popular and well-known job scheduler that many companies use for automating repetitive tasks. Some common use cases are email distribution, report generation, database backups, and software updates. Now let's talk about the utility itself. Cron is made up of three parts: cron jobs, a cron tab, and a daemon called cron D. A cron job is a command or shell script that is run on some fixed schedule. This part of the job indicates the command that cron should execute, rotate log, and this string indicates the schedule on which it should run. The second component is the cron tab. This word actually refers to two separate entities: a CLI program and a configuration file. The CLI program is how a user interacts with cron from their shell. For example, the command cron tab E opens up a text file that contains the user's cron jobs. This text file is what I'm referring to when I say the configuration file. When we talk about a cron tab during this presentation, we mean this config file. Additionally, a computer has one cron tab per user, as well as a system-wide one. Finally, we have the cron daemon, cron D. So what is a daemon? This is a background process. If you remember from our description of cron jobs, they have a schedule. So on this schedule, when it's time to execute a job, cron D will spawn a child process to execute it. So now you know all about cron. It's a ubiquitous tool used by lots of teams. But as you can guess from this slide's title, there are limitations. We can go through some of the most common questions users have when encountering an issue with cron, starting with, did my job start? And did my job complete? These two questions speak to one of the biggest issues with cron. Jobs fail silently. Cron doesn't have any alerting. It attempts to execute the command or script it's given, and if it fails, well, that's now on the user to verify. You can imagine that a job like an evening report not being generated or sent would probably be annoying but manageable. But if your jobs are to back up your database daily or run a security update, this is much more detrimental because it can leave the system in a vulnerable state. We need to know if those jobs ran. Another question users have is, where can I find logs for cron jobs? Well, they aren't centralized, so the answer is complicated. Cron does write job execution logs to a user's syslog, but any other job output, including errors, isn't stored anywhere. To capture job output, a user can either create a log file and direct output to it, or configure the output to be sent to their email. These logs need to be reviewed manually to determine if the job encountered issues, which can also be a tedious process. That brings up another common question. My job didn't run. Is my schedule correct? This is a common issue because writing a schedule can be unintuitive, especially if you've never used it. Let's look at this cron job for rotating logs. The schedule is made up of numbers and asterisks. Off the top of my head, I don't know when this job is meant to run, so let's see how to parse this syntax. Starting from the left, the job occurs on the 0th minute, the second hour. Asterisk means every, so every day, month, and weekday, which means this job runs every night at 2 a.m. You can see how easy it is to make a mistake and write the wrong schedule, leading to jobs running at unexpected times. So, quick recap on what the main problems are. Cron jobs fail silently, cron logs are not centralized, and scheduling syntax is error-prone. These problems are all solvable. If cron jobs fail silently, then you need monitoring that will alert you of failures. If cron logs are found in different places, then those need to be gathered into one place. If scheduling is unclear, then you need a manager to help you schedule. There are services out there that provide monitoring and management of scheduled tasks. Most, you can see, have cron in the name. There are definite benefits to using one of these services. Some offer additional types of monitoring, like uptime monitoring and heartbeat monitoring. They're accessible on the web, and some can even rerun jobs when they fail. But these services do have their drawbacks. Some don't use cron, but build their own cron-like services. You have to transfer any of your existing cron jobs to their platform. Your data isn't your own. It's now being held by a third party. And many don't provide a centralized place for error logging. And that's why we built Sundial. It provides reliable monitoring, a centralized place for error logging, and a convenient job management from a UI. It's open source, self-hosted, and focuses specifically on the cron utility. How does Sundial do all of this? Let's start this explanation by introducing the two main components that make up our architecture. First, the monitoring service. It monitors the execution of cron jobs. It includes a database, task queues, and an app server that exposes an API. It was Dockerized to eliminate dependencies and for a simple and straightforward installation. Second, the linking client. This serves as a link between the monitoring service and the cron tab. It's made up of a lightweight HTTP server and a binary executable that includes a collection of scripts. Sundial can run on one or multiple nodes. For a single node architecture, the monitoring service and the linking client are installed on the same machine. In the multi-node paradigm, the monitoring service only needs to be installed on one node. We'll call this the hub node. If a user wants to monitor and manage cron tabs on additional nodes, also known as remote nodes, the user just has to install the linking client on them. Now that you've been introduced to Sundial, I'll pass it along to Jacob to talk about the first solution Sundial offers, monitoring.
Thanks, Mary. As we are all now aware, Sundial focuses specifically on the monitoring of jobs executed by the cron utility. We therefore need a way for the monitoring service to peer into the user's cron setup. To achieve this, information needs to be sent to the monitoring service at two different times. The first is before job execution. The service needs a prior knowledge of what jobs the user has and, crucially, when they're due to execute. We cannot inform the user that their job did not run if we did not know it was due to run. Second is during job execution. We need to know when jobs start, when they end, and when they encounter errors so that we can report this information back to the user in real time. Providing this information to the monitoring service is the job of the linking client. As Mary said, it serves as the link between the user's cron utility and the monitoring service, handling all communication between the two. Sending information about existing jobs before they execute is the responsibility of the linking client script triggered with the Sundial discover command. The user runs this command on setup to configure the cron utility and the monitoring service to work together. Let's take a look at how this is done. Sundial discover programmatically traverses the cron tab file, sending information to the monitoring service about each job. This information is stored in the database, ensuring that the service has the prior knowledge it needs to function. The second thing Sundial discover does is wrap each existing command in the cron tab file. For example, a cron tab file that originally looked like this will be transformed into this. Looking closer at a specific example from the cron tab, we see that Sundial discover wraps the original line with a Sundial run command. Additionally, we pass in an endpoint key. This acts as an identifier used to link each job in the cron tab file with its corresponding job in the database. So what is Sundial run? Sundial run is another script provided by the linking client. It handles the second type of information we have said the monitoring service needs, information sent during job execution. Let's look again at our example log rotation job. Notice that the original command specified by the user is still included. However, it is now passed in as an argument to Sundial run. When it comes time for the job to be executed, the cron daemon launches Sundial run rather than executing the user-specified command directly. Sundial run performs 3 tasks. First, it sends an HTTP request, referred to as the start ping, to the monitoring service. Next, it executes the passed-in command as a child process. Finally, after the job is completed, it sends an end ping. To summarize, Sundial Discover informs the monitoring service of existing jobs by traversing the cron tab and sending job details via HTTP requests. Additionally, it configures the cron tab to allow communication at runtime. This is done by altering lines to integrate the Sundial run script with each execution of a monitored job. The purpose of Sundial run is to handle communication with the monitoring service during job execution and to execute the user-specified command internally. The combination of these 2 linking client scripts ensures that the monitoring service is provided with all the information it needs to store data about a user's job execution status. This is how Sundial handles monitoring. Or is it? Unfortunately, life is not so simple. While the architecture we've discussed so far provides all the information needed to inform the user about jobs that run, it is lacking in one key area. What if your jobs don't run? In particular, what happens when pings from the linking client don't arrive as expected? Before discussing this, let's first go over some reasons this might occur. System resources could be depleted, preventing cron from initiating the Sundial run script. A job might be running for longer than usual, perhaps because it's processing a larger than normal dataset or it's stuck in an infinite loop. Manual changes to the cron tab may not have been propagated to the monitoring system, and finally, plain old network issues. We want to notify the users when any of these situations occur. However, acting in the event of a ping not arriving is inherently more challenging than acting when it does. Solving this problem is the role of the task queues, which, as we saw earlier, are a part of the monitoring service. The task queues are used to keep track of the time start and end pings are expected to arrive. Each task on the queue is added with a delay and waits for a ping from a monitored job. When the delay elapses, the task triggers, signifying that the ping has not arrived, and the monitoring service performs all necessary operations to inform the user that something has gone wrong. We'll now take a look at 2 examples that go over in detail how communication sent from the Sundial run script and the task queues work together to deliver Sundial's monitoring functionality. Since this is a monitoring application intended to inform users when their jobs are not working, the examples we go over both include a failing job. The first example is a job which does not start, and the second is a job which is encountering a fatal error. Both examples use our favorite cron job, the log rotation script. Recall that the schedule dictates that it should run daily at 2 a.m. On the first night, the server running this job is under unusually high load. Because of this, the cron daemon is failing to start jobs at all, the server does not execute the Sundial run script, and no communication is sent to the monitoring service. The monitoring service implements 2 types of task queue, the start queue and the end queue. This is the start queue. Tasks on this queue wait for the arrival of start pings. As you can see, a task sits at the end of this queue, patiently waiting for the arrival of a start ping associated with the log rotation job. The delay on this task currently sits at 5 seconds to allow some extra time for the start ping to come in, accounting for network latency or high load on the monitoring service. As 5 seconds pass, the start ping will never arrive, causing the task to trigger. The first thing the monitoring service does is add a new task to the queue that waits for the next expected start ping. Since this job runs daily, the delay is set to 24 hours. The monitoring service then notifies the user that their job has failed to run. Depending upon the user's configuration, these notifications would arrive via either Slack or email. Our next example takes place the day after. The system admin has been alerted that their job is failing and wisely adjusted the resources assigned to the server in the hopes of preventing further failures. The cron daemon successfully launches the Sundial run rat log rotation job. The linking client script sends a start ping to the monitoring service, indicating that job execution is about to begin. Since the start ping has successfully arrived, We do not want the task on the start queue to trigger as it did the night before. Therefore, we adjust the delay on this task according to the job's schedule. Once again, as the job runs daily, the delay is set to 24 hours and 5 seconds from now, which includes the 5 seconds extra provided for the start ping to arrive. Additionally, we need to add a task to the end queue. This is the second type of task queue mentioned earlier. Tasks on this queue await the arrival of end pings. The delay on this task is 1 minute. This is set using the tolerable runtime, a value selected by the user that signifies how long is acceptable for their job to run before they are notified. After sending the start ping, Sundial Run begins executing the log rotation script as a child process. Unfortunately, the script encounters an error while executing. Recent infrastructure changes have affected the database connection used to store logs, and overworked devs have forgotten to adjust the script accordingly. In response, Sundial Run sends an end ping to the monitoring service containing data indicating that an error occurred while running the script. The task on the end queue, which still has a remaining delay of 15 seconds, is removed. This prevents the missed end ping logic from being performed. So, the monitoring service now holds a record of the failed job execution status and can notify the user of this failure. Cron jobs fail silently no longer. Now, recall another problem with cron mentioned in the introduction: decentralized error logging. With our current architecture, this is a simple problem to solve. Since the script is run internally as a child process, when Sundial Run encounters the failure, it simply sends all output to the monitoring service for storage. So, in this section, we've seen how the linking client facilitates communication between the cron utility and the monitoring service, both before and during the execution of jobs. The monitoring service recognizes missing pings with the help of the task queues. Combining these two elements allows Sundial to achieve the first two of its stated core features: reliable monitoring of the user's cron jobs and a centralized place for error logging. I will now pass you on to Sofia, who will introduce the implementation of Sundial's third feature: convenient job management orchestrated from the UI.
Thanks, Jacob. Let's get straight into it. Management is the ability to add, delete, and update jobs from the UI of the application. It serves two main purposes. The first is accuracy. Recall that in order to create cron jobs, you must write the schedule using cron syntax, which can be unintuitive and so increases the chance for errors. For example, let's say I'm tasked with automating our monthly reports. As you can see here, the difference between this report being sent once a month versus once a year is a single character. To reduce the possibility of this mistake, we provide a cron schedule translator. When adding or editing a job in the UI, the form provides a human-readable translation of the schedule. As you can see, right below the schedule string, it informs me this means once a month and this once a year. The second purpose for job management is convenience. Users can perform all cron-related tasks from the UI. So the typical workflow for adding a new job requires the user to enter a command into the CLI and then edit the cron tab directly. This is transformed to filling out a form in the UI. So to summarize, the management part of Sundial provides a syntax translator that aims to reduce the occurrence of errors when writing cron schedules, and a convenient UI that allows a user to add, delete, and update their cron tabs across one or multiple nodes from a single UI. With data traveling between components, especially over multiple nodes, it could fail to arrive successfully. So to limit data loss, new data is immediately saved to the database before it's written to the cron tab. This is because the database is the first persistent data store encountered. As you can see, when adding new data in the UI, the flow of information starts with the monitoring service, which includes the database, and then moves outwards towards the cron tab. With data stored both in the monitoring services database and in the cron tab, it's possible for these two to get out of sync. If that occurs, we treat the database as the source of truth, meaning that if a discrepancy exists, the data in the database overwrites the data in the cron tab. Great, so we know where the data is stored. How does the data get from the database to the cron tab? Well, I'll demonstrate with an example, but first recall that Sundial works across multiple nodes. I bring this up because the data flow architecture was highly influenced by the consideration that data may have to travel over the network. With that in mind, let's follow the flow of data after a user adds a job in the UI to a cron tab belonging to a remote node. Following the addition in the UI, the monitoring service sends a request to the listening service. The listening service is one of the components within the linking client that Mary mentioned earlier. It's a lightweight HTTP server that, well, as you could probably guess by the name, listens for incoming requests. When the listening service receives a specific request from the monitoring service, it triggers the linking client's update script. This script issues a request for the new data to the monitoring service's API. The monitoring service sends the new management data as a response, and the update script handles the logic for writing it to the cron tab. Take particular note that the monitoring service does not send management data directly to the listening service, although that would be more direct. The monitoring service instead only sends management data as a response to an API request. We designed the flow of information like this to provide the user the convenience of only having to harden one component, the monitoring service's API. When we say harden, we're referring to the security measures we've put in place that the user has to implement to use Sundial on multiple nodes. Remember the scripts Jacob discussed, discover and run? Both of those issue requests containing sensitive data to the monitoring service's API. So even without management, in order to use Sundial across nodes, the user would have to take security precautions to prevent unauthorized access to the monitoring service's API. And because we designed the management data flow like demonstrated, we're able to use the same API for sending management data, simplifying the setup required of the user. So to recap, management data is transmitted only as a response to a request to the monitoring service's API. It is not sent to the listening service directly. This ensures that only the monitoring service's API is responsible for sensitive data transfer. And because of this, only the monitoring service's API is required to be hardened. I'll briefly explain what those hardening steps are. We use API keys to prevent unauthorized access to the monitoring service's API. And as you may know, API keys must be used in tandem with the HTTPS protocol. So the user has to obtain an SSL certificate for the hub node to run the monitoring service's API on an HTTPS-enabled port. Then, for each remote node, the user must retrieve an API key from the password-protected UI and distribute it to the node via the linking client's registration script. This configures future requests sent from the node to the monitoring services API to include the API key in the header. With these steps, the monitoring services API will authenticate requests it receives and only process authorized requests containing a valid API key. So we could always improve upon security further, but let's move on. We'll review what we've covered in this section. Sundial provides a UI for job management. The dashboard includes a schedule translator, as well as a form that can be used to write data to the cron tab of a local or remote node. This achieves the third core feature we set out to do, convenient and reliable job management from the UI. Now I'll pass it off to David, who's going to take us through the exciting part, the demo.
Thanks, Sophia. Now that we've got a handle on the architecture, let's see Sundial in action.
So here we have a multi-node setup using DigitalOcean, but we could just as easily use Sundial with another provider like AWS. Within our setup, we have one hub server and two remote servers. We've SSH'd into all three, downloaded the linking client scripts on each remote server, and started up the monitoring service on the hub server. Let's take a look at the UI of the monitoring service. On this page, we have a list of all of the monitored machines. We can see that we've already registered the first remote server. So let's register our second remote server. We're going to click Add New Key and copy and paste the script into the command line. We then add the D flag to indicate that we'd like to run our listening service as a background process. Next, we'll answer the prompts for the IP addresses for both the remote server as well as the hub server. Remember, this is done to enable communication between the monitoring service and the linking client. Awesome. We've now successfully registered our second machine. Let's update the machine name. So now that we've added our machines, let's explore the jobs page. Here, we can see a list of our cron jobs. with a drop-down menu to filter which machine they belong to. Prior to this demo, we added the jobs from machine 1 to the monitoring service. On the other hand, machine 2 has no monitored jobs yet. So let's add the cron jobs on our newly registered machine to our monitoring service. As Mary explained earlier, cron tab refers to both the configuration file and a CLI command that comes with Unix-like operating systems. Running cron tab with the L flag will display the contents of the cron tab, which currently consists of 4 cron jobs. By running Sundial Discover, we can go through each cron job and decide if we'd like to add it to our monitoring service. Below, we see the jobs dynamically uploaded in the UI. We can also run Sundial Discover with the A flag to indicate that we'd like to add monitors for all of our jobs. Checking out our cron tab again, we can see that Sundial Discover added the wrapper commands with the endpoint keys to our jobs. Let's add a job to machine 2 by clicking Add New and filling out the form. You'll notice that the English translation of our schedule updates automatically. Going back to machine 2, we'll see that we successfully added the new job to the cron tab. We can also edit and delete jobs from our UI. Here, we'll update a job, delete another, and check that these changes show up in the cron tab. Nice. We can see that we've removed Echo 2 and updated our final job. Finally, let's check out the monitoring pages for some of our jobs here. Here on the top of the page, we see the schedule, command, and status of the monitored job. Below, we have a list of all of the previous runs of a job. Each run displays its execution time, description, and duration. We can also see that these jobs successfully ran based on their color coding. Let's check out another monitor. For this second monitor tracking a longer running job, we can see that end pings are not arriving in time. This description suggests a potential issue causing the job to run slowly. If the system is performing as anticipated and can manage a slower job, we have the option to adjust the monitor's tolerable runtime. On this next monitoring page, we can see that this job is failing. But if we expand the error logs, we can see more information about the jobs to help us troubleshoot. It looks like this script has an invalid command on line 3. Good thing we have these error logs. Finally, going back to the main page, we can see that our slow script from the previous monitor is now running successfully since we adjusted the tolerable runtime. So to recap, first, we registered all of the remote servers with the monitoring service. Second, we added jobs from the remote servers to the monitoring service using Sundial Discover. Third, we created, edited, and deleted jobs from the UI. And finally, fourth, we examined monitoring and error log information on these jobs.
So now that we've seen Sundial in action, let's review the load testing that we did. Load testing was performed on the Sundial application to answer one key question. How many concurrent jobs can the monitoring service handle? In interpreting the results, we also consider the worst case scenario and assume that these jobs are running every minute, the minimum interval offered by the cron utility. Since our application is self-hosted, we need to decide the hardware to deploy it on while conducting our tests. We chose the minimum available DigitalOcean droplet, a virtual machine with the following specs. To perform the tests, we used the Grafana K6 open source load testing tool, running on one of our developers' local machines. Our testing script was designed to mimic the execution of the Sundial run script, sending a start ping, then waiting for a set period, and then sending an end ping. For each round of load testing, the script is executed concurrently a set number of times. So there are two variables in our tests: the waiting period, modeling job duration, and the number of iterations, modeling total concurrent jobs. In this presentation, we will discuss the results gathered from the jobs, which last 55 seconds. Let's take a look at our objectives. We want all requests sent to the monitoring service to be processed successfully. We also want to avoid overlapping jobs. These are jobs which do not finish executing before their next scheduled execution time. This results in multiple instances of the job running at the same time. We convert this objective into a quantifiable target by imposing a restriction on response time. In the case of jobs which run every minute, we calculate this imposed restriction with the shown equation. Response time plus job duration is smaller than 60 seconds. In our case, the job duration is 55 seconds, and rearranging this equation results in a maximum acceptable response time of 5 seconds. The test was run all the way from 10 to 150 concurrent jobs. Considering the success conditions, we found that the failure rate was 0%. No requests were processed unsuccessfully, even all the way up to the 150 concurrent job mark. As stated, to meet the overlapping jobs condition, we need response times to be less than 5 seconds. Reading from the graph and considering the 95th percentile line, we find a 33 job limit. So what does all this mean for our application? Sundial was found to handle 33 concurrent jobs. It's worth restating here that this is assuming the worst case scenario of jobs that run concurrently every single minute, not the usual situation. If jobs are spread out, the Sundial architecture can manage the monitoring of many more jobs than this. Since this droplet costs $6 per month, this works out to about 18 cents per monitor per month. Cronitor, a paid alternative, is $2 per monitor per month. So how can these results be improved? Well, the user could take some steps, such as batching or staggering their jobs. Additionally, we could move the task queues Jacob told us about to a cache. This would take a significant load off of our database and provide snappier queries. And speaking of improvements, open source projects are never done evolving, and Sundial is no exception. Additional future goals include adding greater user control over historical data for run rotations, user settings for notifications, heartbeat and performance monitoring, and improving upon security protocol to better support our public deployment option. Thanks for listening to our presentation. Now we can open up the floor to any questions. Cool. So let's take a look here. Looks like we have one question. Why did you choose to make the database the source of truth rather than the cron tab file? Does anyone want to take that?
Sure. This is a great question. I think it could be certainly implemented either way. The main driving force, honestly, I think was simplicity. You can imagine, well, in order to implement it so that the cron tab is the source of truth, we would need, when updates occur, for the existing cron tab to be sent over to the monitoring service. Otherwise, how would we know which updates we need to add to the cron tab? We need to know its existing state first. But if Sundial is being used by multiple users, you can imagine a scenario where, say, Mary makes a change directly in the cron tab without going through the Sundial UI. Then Jacob comes along and makes a change in the UI, and on the same job, and a conflict is detected. In that case, which update do you want to keep? The one made in the UI or the one made in the cron tab? This could be implemented potentially as well by displaying to the user when this occurs and saying an update has already been made in the cron tab. Would you like to keep your current change or keep the old change? But all of this adds additional load onto the monitoring system, as well as additional network load sending the cron tab over to the monitoring system before updates happen in the first place. We went for the simpler option of relying on the database as the source of truth. And if our application is being used always as the means in which the user interacts with the cron tab, then this shouldn't cause any problems.
You may have noticed that we had a 0% response failure rate come up to the 150 concurrent jobs mark with our load testing. So this would naturally bring up the question of how many concurrent jobs can our monitoring system handle before it fails to handle all requests. So in some of our additional testing, requests started failing at about the 200 concurrent job mark. Only a minority of requests failed, something like 10%, but this would certainly be considered unacceptable for our use case. Thank you all for attending. Appreciate it. And if you have any other further questions, feel free to reach out to us on Slack.
Thanks a lot, everyone.